Bismillahirrahmanirrahim. So today we will continue with our study of the DHSY paper. There are lots of things in it. I am just going to focus on some of the crucial things. So the first section was basically about exploratory data analysis. Now the second part is about comparing the three models, H, B and W, and that's what we are going to focus on today. One thing that is important is that basically you can never prove that a model is true. You can only prove that it is wrong. So a good econometrician is someone who knows how to disprove models. Now the main criticism that Henry makes of conventional methodology is that people find models to be good because they do not test them. Yani, by not making the tests, you say that this is a good model, and if you actually tested it, you will find that the model is not good. So the process which Henry recommends is that you take a model and then you subject it to the maximum number of tests, and if the model passes all the tests, then it is a candidate for a good model. Most people simply don't test. So the thing that we need to, the thing that I will try to focus on in this lecture is how do you test a model. So thoroughly tested model has some chance of being right, and normally the way that people are doing modeling, they do not test the models at all, and even when they test and they find that Darwin-Watson is wrong, they say, okay, let's not just publish this, let's not write down the Darwin-Watson statistic because it is harmful to our model. So instead of trying to test models, what they do is they try not to test models. That is one part of the conventional methodology. And in Henry's view, the hardest test is the out-of-sample forecast. However, all of these ideas are related to the nominalist view of econometrics, and what I'm trying to teach is the realist view of econometrics. So these are very, very different, and in my paper also talk which is recorded called Methodological Mistakes and Econometric Consequences, I have explained this distinction and how these two lead to entirely different ways of doing econometrics. But today I won't concentrate on this issue, I will just follow what Henry is doing. But I would like to say that not everything in Henry is right. In fact, Henry is very much a nominalist. He just looks at the patterns. Basically, the key difference is that is there a good fit? If there is a good fit, then that's what you're looking for. But a realist is not looking for a good fit. He's looking for something else, which we will see later. So basically, the last lecture was about the exploratory data analysis which Henry has done on this data. This leads to several ideas about how the data behaves. Now the next step is to run the regression model, and basically I will go to briefly review this. Okay, so this is what we have covered, that there are many studies of the consumption function. They have similar theories, similar data, similar regression methodology, but they all come up with different results in terms of marginal propensity to consume, both long run and short run, in terms of lag reactions, multipliers, and long run responses. So all three of the models, H, B and W, produce different answers to these crucial questions. So if we want to do economic policy, that depends exactly on these things. So we have no reliable guide to economic policy from these different functions. Actually, Henry, after developing this, he became advisor to the monetary authority in UK, and basically he developed the consumption function and the money demand function, and he would advise them on how to conduct monetary policy. So he writes one of his papers, which I haven't been able to trace, is how I lost millions of pounds, because basically what the bank has to do, it has to forecast what the consumer demand is going to be, and basically the job, according to the Keynesian theory, the job of the monetary policy is to make sure that the money supply is just right. If it is too high, it will lead to inflation. If it is too low, it will lead to unemployment. And exactly at the right point, you will have zero inflation and zero unemployment. And that was the original theory. It has been made more complex, but roughly speaking, the general idea is still this. So basically, the way that this is done is that you forecast the aggregate demand, and if it is too low, then you increase your money supply. If it is too high, that is basically you know what is the potential amount of the potential output, what is the amount that the economy can produce at full employment. So this is your target demand level. If the demand is higher than what the economy can produce, that will lead to inflation, so you want to reduce the money supply and so on. So basically what he says in this article is that we made a mistake in the forecasting methodology, and therefore we reduced the money supply when we should have expanded it, and that caused losses of millions of pounds. So these things are important, and they make a difference, but current econometric methodology does not give you the answers that you need in order to make policy. So basically what Henry does is that he standardizes all the models. Now this is rather complex, but we don't need to worry about it. That's not one of the key contributions of the paper. Basically, in terms of understanding it for ourselves and for using this methodology, you can think it in a very simple way. Every theory tells you that these are the variables which matter, and that's all. So now you start, so we have three different theories, they give us three different sets of variables, and now construct models based on different collections of variables. So you can have three different models with three different collections of variables. Okay. Okay, so the three different models are here. There's the Henry model. Henry model has the consumption is based on income, current income, last period's consumption, plus seasonal variables, plus time varying seasonals. So this is the Henry model. Now one very important thing that we are going to need to understand is that if you put that how do we reduce models? Actually there is no good way, no unique way, no real guidance on. So when we have a big model, many variables will be insignificant. So what should you do? Think now that suppose that two variables are insignificant, x1 and x2 in a large model. So should we drop both of them? This is the point that I want you to understand, that no, you can't drop both of them, because the t statistic which you see is assessing what will happen to the equation if x1 goes away. So now suppose that x1 and x2 are highly collinear variables. They are almost the same variable. They measure almost the same thing. Then the t statistic will tell you that if I remove x1, nothing will happen because x2 is there to protect what x1 was doing. Similarly, the statistic for x2 will show that this variable is not significant because x2 is covering for it. If you remove x2, nothing will happen to the equation because the x1 variable covers. So these are substitutes for each other. If you have one, you don't need the other. So the t statistic only tests the particular variable in isolation to see if this variable important, and it gives the right answer that this variable x2 is not important because x1 is already present. And similarly, the t statistic for x1 will say exactly the same thing. x1 is not important. But you can't take both of these messages. Oh, the t is telling us that x1 is not important and x2 is not important, so we can drop both of them. No, that's the wrong conclusion, although it seems quite obvious. I mean, people, especially who don't have experience with this, will say, oh, naturally, you should drop all the variables with the insignificant t's. You can't do that, yes. Yeah, you have this multicollinearity theory. Doesn't work very well, doesn't help. So this is not the right line to think about that particular issue. Now, there is some theory along those lines, but it doesn't work very well in practice. So basically that means that what we do when we run an encompassing analysis, we will have a large variable, 20 variables. Of these, 10 are insignificant and 10 are significant. Now what do we do next? There is no one way that you do is you take the least significant variable and you drop that, and then you run the equation again, and you keep. This is called stepwise regression, and that also doesn't work very well. Now, actually, after a lot of experience and a lot of experimentation, Henry has developed this program called Autometrics. And Autometrics does this procedure of selection by an automatic algorithm. You just feed it all the variables in it. Even the case which somebody mentioned, that suppose there are more variables than there are observations. So this model can, this program can handle that situation also. There is a technique which is used in this situation, which is called, I forgot the name now. But anyway, that's not our goal for today. So, in this model, Henry started with y, ct minus 1 and seasonals only. And then he wanted to improve this model. This is a standard bottom-up methodology which everybody follows and which Henry is going to recommend against. He wants to follow the top-down. But the standard bottom method, you start with an equation and then you test for misspecifications. So he found that fourth order autocorrelation is significant misspecification. Omitted 4-period lags, which means yt minus 4 and ct minus 4 or 5 is important. So both of those variables are significant. So and then time varying seasonals, that's also significant if you put it in. So now you have 3 choices. You can improve the model by putting in a fourth order autocorrelation term, or you can improve it by putting in yt minus 4 and ct minus 5, or you can put in time varying seasonals. And doing some statistical tests, he finds that the time varying seasonals are the best statistically. Now, from the point of view of real econometrics, which is what I want to teach, and this is exactly nominalist, that you look for the best fit. Realist economist says that what is the underlying, we are looking for an underlying mechanism. So, which is driving the world. We are looking for some real phenomena. So this time-varying seasonal is completely ridiculous. We would reject the model without any actual trying to run the fit, because the way you estimate this model estimated, pretty soon, if time runs on, because these are time trends, it turns out that the consumption will become greater than the income. So this is obviously a wrong model. It doesn't correspond to the real world, so it should be rejected on those grounds without doing any fitting. Oh, well, if this model with the time varying seasonals is correct, it has a time trend in the constant, and the constant keeps increasing so fast that eventually it becomes bigger than the GNP. Although in the short run it remains, it's a good fit, but in the long run it. So now he is also providing a critique of the H model. So he says that the seasonal pattern is ad hoc. You just put in something which fits the time varying seasonals, but there are many other ways that you could think about seasonality. The LRMPC, long run marginal propensity to consume, is equal to, let's see, the coefficient of y divided by 1 minus the coefficient of consumption, right? That would be the long run MPC. Basically, how you calculate that is that in the long run, you say that Ct is equal to Ct minus 1 in the long run equilibrium. So then you transfer Ct minus 1 to the other side and you get 1 minus beta, and then you divide through and you get. So now what he says is that the coefficient on Ct minus 1 was very high. If you remember correctly, that the Ct has a very strong correlation with each other, and 99%. So basically the coefficient of Ct minus 1 was very close to 1. So when you look at and the coefficient of y was about 0.2. So 0.2 over 1 minus 0.9. Now if, because of this 1 minus 0.9, this is a very small number, 0.1. So if the coefficient changes by a little bit, there's a huge variation in the long run marginal propensity to consume, and that means that the coefficient is unstable. You can't estimate it very precisely because. So the short run MPC was in this model 20%, and the long run was 84%. So it's very different, very small. Oh, sorry. In this one, that's not the case. So anyway, the numbers are not very much like what we think. Like 20% is not a decent estimate of the marginal propensity to consume. It's too low, according to our understanding. Again, this is a real criticism. It bases on our knowledge of the real world and how people spend their income. He also says that testing is not sufficient. Forecast testing has not been done. Stability testing has not been done. This is a very important thing. I mean, this is what's done by Chow test, for example. You split the regression in half. You estimate the equation across the two, and you try to see if the coefficients are stable. If the coefficients are not stable, it means that the regression model is changing in time. And you can test for significant difference. Now, one short note here is that the Chow test is not a very good method to do this, because the Chow test assumes that the variance is the same in both parts, the first half and the second half. And normally, when structural change happens, then both the variance and the coefficients change. And very strangely, when we examine this, S. Fandiar, Masumi and myself, we found that nobody has developed a test. So in fact, we wrote this paper 17 years ago, a long, long time ago, but for some reason we never got around to publishing it. So recently it has been published a few years ago. And so now we have the test which provides for a test in which we have real structural change, means the coefficients also change and the variance also changes. This too is not enough, because what you really need, this works, the Chow test, or the what we call the MZ test, Masumi Zaman, works if you know the date of the structural change, because you specify the time and then you divide the regression into two parts and then you carry out the test for change. If you don't know, then this cannot be used. So in that case, what we have is and that is that's the only practical thing, the rolling Chow test. The rolling Chow test divides the sample at every single point and then does the test. Now, some of the analysis of this test, the rolling Chow test, shows that if you go too close to the endpoints, you get into trouble. That is because as you become, for example, if you come, like suppose you have a sample size of 100 and you have your consumption function, which is what we have. Then you can test it at the midpoint, which is 50, or you can test it 25. Or what the rolling test will do is that you start at, for example, 10th observation and do the test for the first 10 against the bottom 90, and then the first 11 against the 89, and so on, and run all of those tests. So that's called the rolling Chow test. And then you take the maximum of those values as your soup Chow statistic, and if the maximum is too big, then you reject the null hypothesis of structural of stability, and if the maximum is small enough, then you accept the null hypothesis. Now the question is, what should the critical value be? So basically, in fact, this test was proposed a long time ago, but nobody, Goldfeld-Quant, I think, proposed this. But nobody could use it because they didn't know the critical values. And then Andrews wrote a paper which showed that this test had optimality properties, and also he calculated the asymptotic critical values for this test based on Brownian motion and things like that. Now, the thing is that what we did is that we said that the asymptotic critical values are not very good, but by using a bootstrapping technique, you can easily calculate finite sample critical values. So that is and find out if these are significant or not. And that is something which is very important for people to learn, how to use bootstrapping to calculate critical values for tests. This is a general thing. You can take any test for any model and use bootstrapping to calculate its critical values. To explain how important this is, you see, why did the Durbin-Watson test? Durbin-Watson test has, at some point, it had the maximum number of citations in the whole literature of econometrics. I think it's no longer holding that record, but for some time it did. Why was that? Because nobody knew how to test for autocorrelation, because if you set up the test statistic, you find that it depends on X, the matrix of regresses, which is T by K. So you can't calculate a distribution for it because there are so many numbers in that X matrix that, and the test depends on every one of them. So what the Durbin and Watson did was they calculated the bounds based on the eigenvalues, showing that there is a maximum possible value and a minimum possible value, and those maximum and minimum were independent of X. So that means that you can calculate the critical values of the Durbin-Watson test without specifying what is the matrix of regressors. And that was a big breakthrough because nobody knew how to calculate the critical values. Nowadays, the paper is completely useless because for any X matrix, we can just feed it into the computer and get the critical value for that X matrix without any difficulty. So now the Durbin-Watson is just and actually, as I have shown in some in my book, for example, Durbin-Watson is a very bad test, and it has poor power properties, and there are better tests which are more powerful tests against autocorrelation. So what I want you to do, one thing that needs to be done, which I won't explain here, because I'm taking a broad focus, is that you should learn how to calculate critical values for tests using bootstrapping methods, because this is completely general. You can do it for any test in any regression model, and then you are free. You don't need to calculate. And the Andrews paper is also of no significance, although it made a very big impact at the time, because he again did something which was very essential and needed, and nobody knew how to do, which is that the structural change hypothesis with unknown breakpoint. He developed a test and a theory for it. So stability test is the rolling Chow test, but as I said, rolling Chow test is not a good test because it assumes that the variances remain the same regardless of what else is happening. And so we have in another paper recommended the SOUP-MZ test, that if you look at this MZ statistic and you run the rolling, the same thing, you take the breakpoints and calculate it at each breakpoint and then take the maximum. Now, one thing that I was saying but I forgot in the middle, is that Andrews' paper shows that if you go too close to the endpoints, you get into trouble. The reason is that, for example, if you take t equals 10 or 5, that with a very small sample, you have a very high variation in the estimates. The estimates are very imprecise and very unstable and have a very high variance. So you can quickly and easily get a maximum just by chance at the endpoint. So basically then he says that at least you should omit 10% of the sample. This is the minimum for safety. So we would not, and if you have 3 variables in your model, then technically you can start at 5, the rolling Chow test, but because you have 3 plus 1 for the variance and plus 1 for, but and so you can start setting by 5 and 95 and then 6 but this is not a good idea. You should start at 10 and possibly you should be even more, like 15 or 20. So you can start your rolling Chow test at breakpoint t equals 20 and go up to t equals 80. That would be fairly safe. It avoids the problem of having unstable breakpoints near the ends. So the rolling Chow test is very important stability test, and in fact it should be rolling MZ test. Again, autocorrelation tests, he is very strongly against Durbin-Watson. He says that one should use the Haussmann test, which allows for lagged regressors, but that's not really a good test either. Neither Haussmann nor Durbin-Watson are good tests because they're both locally most powerful tests, which are not generally good principles, and there are better tests available for autocorrelation, and similarly for heteroscedasticity and for many other diseases of the regression model. You need to do tests. So that's what DHSY are doing as a criticism of the Henry model. Okay, now the Ball model, which is the B model, is regressing consumption on income and lagged consumption, and it's actually quite similar to the Henry model, except for the fact that it uses seasonal adjustment. So what Henry is doing to do the he does the estimation, he puts in seasonal dummies and then time varying seasonal. So that's one way of taking care of seasonality. But he has the same two variables, y and c minus 1. So here the B model has consumption, seasonally adjusted consumption on seasonally adjustment income and seasonally adjustment consumption with a time lag. He also says that we should take the government expenditures out of Y and C. That turns out not to matter. The same kind of result comes in with G and without G. So basically the Henry model, the H and B model are different only in terms of how they treat seasonal adjustment. So it turns out that the short run and long run marginal propensity to consume in this model are quite similar to the Henry simple model, meaning with seasonals but not with time varying seasonals, which is very easy to understand because they both use basically the same model, but one uses dummies instead of seasonal adjustment. Okay, so the W model uses the percentage change in consumption and regresses it on the percentage change in income and the percentage change in lagged income. So this is different from the other two because it doesn't have C minus 1. Instead of C minus 1, it has Y minus 1. Now, when you look at this, the estimates, you find that the this model has no static equilibrium. That's because the model, when estimated, you have percentage change in consumption is equal to a constant plus these two variables. Now, suppose in a stationary equilibrium, dy and dyt minus 1 will both be 0 because there's no change. That's what stationary means. So, but that means that the consumption will be, percentage change in consumption will be equal to the constant, which happens to be non-zero. So it means that the income will remain fixed and the consumption will keep increasing. So that's again a very strange result. And again, on the basis of real econometrics, we would reject the model on those grounds already. They're saying that this doesn't correspond to our intuition about how the real world works. If the income remains long run stationary, then consumption cannot have an increasing trend. Okay, so the next step is that he translates all these models to a common model. I'm not going to go through the details of that. Okay, so basically the original Henry model is in 813 in the paper, which I have, and I might show you later. And that is replaced by 821, which is the numbering in the DHSY paper. And the regression is based consumption on income, lag consumption, 3 seasonal dummies, 4 time varying seasonals. When you put in the time, then you don't have this dummy problem. So all 4 dummies can be put in without causing the dummy trap. You'll have to think about why that works. And then there is one more dummy variable, D68. The D68 dummy was justified on the ground that in 1968 first quarter, the government announced that there will be a special temporary tax for some particular purpose in the second quarter of 68. So as a result, people who were going to make big purchases would shift the purchases to be early or late. So it turned out that you can see that consumption jumped by a little bit in the first quarter and went down by about the same amount in the second quarter. So people shifted some purchases. Okay, so in this model, fourth order autocorrelation is present, and if you do a forecast test, remember that in this case we are holding some portion of the data outside the estimation. So forecast test rejects this model. So this is the 13 equation, which was original Henry model. And the SRMPC is 0.19, the coefficient of y, and the LRMPC is 0.19 over 1 minus 0.22, or about 0.8. R squared is 0.998. One thing to keep in mind is the sigma hat, because that's a better measure of fit. So the sigma hat is 17.6. Durbin-Watson is 2.2, which is close to 2, which is no autocorrelation. But as we have said, the Durbin-Watson is not a good test, A, and B, this model doesn't qualify because it has lagged consumption. So Durbin-Watson is biased. This is the analog of the Durbin-Watson model, equation 21, which has 0.20, which is not different from 0.19. 0.22 has increased to 0.35. Then there's this D0, that's the 1968 quarter 1 dummy. Oh, actually what he did was he did dt minus 1 minus dt, which means basically you are switching you add 1 to 68 1 and subtract from 68 2. So 83 is the amount of consumption that was added to 68 1 and subtracted from 68 2. So this is shifting of expenditure. Then you have 3 time varying 3 seasonals, Q1, Q2 and Q3, and then you have 3 time varying seasonals. The coefficients are the standard errors, and the numbers in bracket. So which ones, who can tell me whether the constant is significant or not? What about the MPC? Is it significant or not? MPC is 0.20, standard error is 0.05. Is it significant? How do you know it's not significant? How do you tell whether this is significant or not? तो डिवाइड करेंगे तो क्या मिलेगा? Exactly, 2 standard errors. So 0.20 is 4 standard errors, so it is significant. The CT minus coefficient is also significant. It's about 3 standard errors. DT0, that's also significant. Q1T is also significant. Q2T is not significant because 74 is not far away from 57. Q3 is again very significant, 187 and 38. The time trend is highly significant. And the first time varying seasonal is highly significant, but the other 2 are not. Alright, so then we do a test for the forecast errors, and that one rejects the null. Okay, so now in equation 814 is the original ball equation, and he translated in 2 ways. One is y and c minus 1, and then he adds the seasonal dummies. So this is almost the same as the Henry simple model without the time varying seasonals. And the other method is instead of C minus 1, he puts in C minus 4 and also puts in the first difference of Y. Now, YC minus 4, well, basically he argues, and we saw that in the preliminary exploratory data analysis, that seasonal adjustment is like taking C and subtracting CT minus 4 from it. So, you should also put in, basically the seasonal adjustment of Y is to take YT and subtract YT minus 4 from it. So this is the model that the seasonal adjustment. So basically seasonal adjustment is like the Henry model, except that instead of putting in lags of C, you put in one first order lag, you put in the fourth order lag, and also you add a fourth order lag of Y. And that's the counterpart of doing seasonal adjustment. So he says that when you test it, you find that fourth order autocorrelation is still present, which means that one very important point that one thing that we are trying to do is to learn how to reject models. So if you have autocorrelation, that means that the model is rejected. This is very important to understand. You can't say, especially because econometrics texts don't make this point clearly. They just say, okay, you had an autocorrelation term. No. What is autocorrelation? Suppose you have C equals alpha plus beta Y plus epsilon. And now this is a static model. What does it mean? It means everything happens at time period T. What happened last period does not matter. Now, if you have autocorrelation, it means that what happened last period matters. Yani epsilon T minus 1 is what you can say, the disequilibrium in the last period, the lack of balance. You say C is equal to alpha Y, that was the planned consumption, exactly the right level according to the consumption, but there was some error, there was some disequilibrium. The people did not consume what they were supposed to. So this variable, this measures the disequilibrium in the last period, and that is a relevant factor. So the first implication of autocorrelation is that the model is dynamic and not a static model. It means that the model is rejected, the static model is rejected. Now the right thing to do in this situation is to say that, okay, since the model is dynamic, since the last period matters, so we should put in everything from the last period, which means we should put in CT minus 1 and YT minus 1. And it turns out that autocorrelation is a special case of this fully dynamic second order, first order model. So when you have autocorrelation, it means that you must put in YT minus 1 and CT minus 1, or all the lags of the regressors. And that's what the encompassing approach says, actually. That if there is an effect coming from the last period, you don't know that it's the error. It could be any of the variables from the last period. So the big model, which covers all possibilities, is to put in all regressors with one lag. No, you don't need the error with the lag, because once you have the variables, function of those things is the error. So error is unnecessary. So basically then he says that the analog of the W model is D4C, the fourth order lag of C, which means CT minus 4. That's the seasonally adjusted consumption on seasonally adjusted income, and then one lag of seasonally adjusted income. This is exactly the Wall model. except that seasonal adjustment has been replaced by D4. And that is equation 824. Okay, so 14 was the ball model, and he first estimated these two models, 22 and 23, but this is the final equation, that delta 4 of C is like the seasonally adjusted consumption, delta 4 of Y is seasonally adjusted income, and then they have one lag of seasonally adjusted income, which is exactly the W model, and then you put in the dummy for 68.1. Alright, so then he argues that this model is like the W model in the sense that it gives similar estimates. There's a technical point here which I will ignore. There is one important technical point here which I don't want to ignore. Now, one thing that he is saying is that look at this equation 24. In equation 24, the constant is changed a lot from the ball model. So why did this happen? So he estimates the unrestricted equivalent of 24. This is an important point. What is the unrestricted model? Okay, so this is very important. Let's look at this model 24 and this 30. And I want to explain what is the unrestricted model, because this is a very important part of the Henry methodology. Here, 24, equation 24, we have delta 4 Ct minus 1, delta 4 Ct. This is exactly Ct minus Ct minus 4. Okay. Now, I can take this Ct minus 4 to the other side. Right. So, what it means is that if I run this regression on Ct with Ct minus 4 as a regressor, then my 24 is saying that that will have a coefficient of 1. So that's called a restricted model. Now if I just put Ct minus 4 without any restrictions, then that's the unrestricted model. So the unrestricted model includes as a special case this 24, because if the coefficient comes out 1, then it's the same as 24. If it comes out different from 1, then it's different. So it's a more general model. That's similarly for delta 4 yt, this is yt minus 4. So our equation here is saying that delta 4 Ct is equal to 0.34 yt minus 0.34 yt minus 4. So there is a restriction. If I put in yt and yt minus 4, and then I say that the coefficient of yt minus 4 is exactly negative and equal to the coefficient of yt, that's a restriction, linear restriction. We know how to impose such restrictions, but the unrestricted model doesn't impose this restriction. So we just put in yt and yt minus 4 and we estimate, and if it turns out that the two coefficients are similar in size and opposite in sign, then we say okay, this restricted model is correct. But if they are very different, then we say okay, restricted model is not correct. So that is exactly the general to simple principle. This model is a special case of an unrestricted model. So estimate the unrestricted model. If the two coefficients of yt and yt minus 4 are significantly different from each other, then you reject the restricted model and you have a different model. Yes? That's one reason, but also the other reason is that the ball model uses seasonal adjustment, and what Henry argues is that seasonal adjustment is equivalent to fourth period lags, because he wants to put everything into a common framework. So if I want to test W against H, then if I use seasonally adjusted variables in one and non-seasonally adjusted in the other, then these two models are not nested models. This is quarterly data. So if they are not nested models, then I can't use this F-test technique. So quarterly data 1 year ago, same quarter, exactly. So the restricted models versus the unrestricted model. Okay, so now we go here. So you see, you look at this model 0.32 yt minus 0.33 yt minus 4. This shows that the restriction is good. Yani the two model numbers are almost the same and opposite. So we are not the restrict. So if we take this as the general model, we can reduce this to the simple model in the previous one. Similarly, if you look at Ct minus 4, it has a coefficient which is very close to 1 again. So again, that means that that's good, the original model. And again, the delta 1 yt and the delta 1 yt minus 4, again these two numbers are similar and opposite in sign. So all of these things are good. So the restricted model is almost the same as the unrestricted model. The section on multicollinearity. This section has only one point that he is making. What he is saying is that people criticize my encompassing methodology by saying that if we put in all the variables, everything will become insignificant and then we won't know what to do. And so he argues that this is not always the case, and he shows this by looking at this equation 27 and 28. In 27, you have yt, delta 1 yt and ct minus 4 as the variables. So he says, okay, take all of these variables and put in fourth lag of every single variable that you see here. So yt is there, so we put in yt minus 4 in 28, and we put in delta 1 yt minus 4 because delta 1 yt is there, and then we put in ct minus 8 because ct minus 4 is there, and other variables are not so important. So he says, okay, we have doubled the number of variables, but instead of losing significance, we find that significance improves for everything. So basically that's the main argument that he is making here. He says, patently, despite including 3 more regressors, the t-values for y1, delta 1 y and ct minus 4 are all considerably larger in 28, and the trend coefficient has become negligible in 28. Kya? No, that's not. It's not. Generally true. Generally, it's true that the more variables you add, the less significant. But in special cases, things can be different, and this is one of those special cases. That what is happening here is that the seasonality is better explained by 4-period lags on the consumption and income rather than the time trend. And this is exactly what this equation is saying, because time trend is highly significant in 27 but is not significant in 28. So one important remark that Henry makes, which is very significant from our point of view of real econometrics is that trend coefficient has become negligible in 28 and reveals the possibility of explaining the behavior of C by economic variables alone. You see, this is when we put in a time trend, we haven't got any explanation. We are just doing ad hoc fitting. But if you put in CT minus 4, that says that what happened 4 period ago is relevant to what's happening today, and that has a possibility of interpretation. This is only partly true because Henry is not a real realist. What he does is he says, okay, the thing that is good is a good fitting model, and it should also have an interpretation. But what interpretation it has doesn't really matter very much. It can have this or that or the other. What the realist says is that the interpretation is the whole thing. That is the only thing which matters. So this is the difference between Henry methodology and real methodology. But Henry is concerned about interpretations and about match to theory. He understands that if you don't have a match to theory, you have a problem. But as long as it matches a theory, any theory, he is happy. He doesn't really care that. He doesn't really think of the relation between the equation and the theory. So here this remark is very significant, that when we put in fourth period lags of the variables, the time period becomes insignificant. So it means that there's a possibility of a real explanation based on fourth period lags, whereas there's no possibility with just a time trend. Because why does consumption have a time trend? That's a real question that needs to be answered. क्या हुआ? No, but what I'm saying here is that if you put in T, it gets, in addition to all of the economic variables, time trend is significant. So why is that? I mean, we are explaining consumption that it is a portion of the income, but in addition to that, it also has a time trend. This doesn't make sense. So now the selection of the best equation. This is very important. Now 28 encompasses 23 and allows immediate rejection of the latter. This is a very important. Okay, wait. Let's go to 25. Okay, this is the encompassing equation 25. It has all of the variables in all three equations, and so every one of the three H, B, and W models is a special case of this equation 25. So that's going to be our goal, to estimate and then to find out which one is best according to the tests. So, but before we do that, he says that let's look at 28. 28 is this equation where we just put in fourth period lags of everything. And he says that 28 allows us to reject 23. This is the remark that I want you to understand. Here's 23a, but I want to go to 23. Yeah, this is 23. So in 23 we have C on Y, delta 1 Y, CT minus 4, 3 seasonal dummies and a 68 1 quarterly dummy. So how does 28 allow us to reject 23? This is 23. Now 27 is an analog of 23. It's a little bit different, and this is also an important remark here. Let's look at 23. Okay, so what's the difference between 23 and 27? Can you tell? Look at this. It has yt, delta 1 yt, ct minus 4, forget about the 68 dummy, and 3 seasonal dummies. Yt, delta 1 yt, ct minus 4, 3 seasonals. Okay, now we go to 27. Okay, so what's different here? The trend, exactly. So, to illustrate these points, consider the following estimate of a special case of 25, in which this is the same equation as 23, but the trend is there. So, why does 27 immediately demonstrate some misspecification of 23? We're saying after we estimate 27, we know that 23 is wrong. This is the key thing that we need to learn, how to say that an equation is wrong. Because we can never say an equation is right, but we do know how to say equations are wrong. So how do we reject equations? So Henry is saying that 27 allows us to reject 23. Why is he saying that? How do we know that? Yes, on the basis of trend, but what about the trend? Data हमने देखा तो उससे क्या फर्क पड़ता है? We are talking about how did 27 allow us to reject 23. We don't need to look at it because the key is that there is a missing trend. But what is it about the missing trend that allows us to reject? Exactly. The trend here is significant. The coefficient is 13, the standard error is 4. So what we can say is that there is a missing important variable in 23. Because something very simple, the time trend, you put it in, it's significant. It means that that we can improve the equation. Now, if we can improve the equation itself is not a good equation. Now, it doesn't mean that trend is important. This is very important. I mean, you can reject, but you cannot accept. So, this equation doesn't allow us to say that trend is an important variable. All it says is that there is something important that is missing from 23. Because we know that we can improve. हाँ, इसमें तो वो नहीं आ रहा है, यानी 1 नहीं आ रहा है. This is not the wall model in which you have this. This is the ball model, B model. In the B model you have. So this is very important. Whenever you find a regressor which is significant, then you can reject the model which doesn't include that regressor, but you cannot accept the model which includes that regressor. So the trend itself is, and this is a very common situation, it is proxying for something which is missing from the equation. It is not by itself necessarily the important variable. Any variable, if there is anything significant missing, and you put anything which correlates with the missing thing, it will become significant. So it will pick up that effect. So all we can say is that something important is missing, but what it is, we cannot say. Okay, so that's one important point. Now, okay, so this is the big equation, the encompassing equation, which is estimated by Henry, by DHSY actually. So it has yt, ct minus 1, ct minus 4, yt minus 4, delta 1 yt minus 4, and then the dummy and 4-period lag on that dummy. Time trend with a lag is the same as time trend, so that doesn't come in. 3 seasonal dummies, and 4 time varying seasonals. No? 4th तो इसने नहीं डाला, क्या वजह है इसकी? अच्छा, if you put in a time trend, then you cannot put in the 4th time varying seasonal. Either you put in 4 time varying seasonals, or if you put in a time trend, then you can only put 3 time varying seasonals. Alright, so well, if you take Q1t plus Q2t plus Q3t plus Q4t, that is equal to t. So those 5 variables are perfectly multicollinear. You can have only 4 of them, any 4 of them, but not all 5. So now he says that the fit of 29 is little better than either 21 or 28. 29, the sigma hat is 36.2. (28) is 38.7. So there has been a small drop in the standard error, but not much. So this means that putting in all of those additional variables has not helped a lot over 28. The key thing is that we now test the restrictions. So, for example, one of the models, the time varying seasons don't matter, so what we would say is that take the t 7.6 coefficient and the q1t, which has 2.95, and q2t 3.88 and q3t 4.63, and do a test for all 5 of these variables being not present. So you know how to do that test? No? This is one of the questions on the comprehensive. How do you do that? You run the 2 regressions, one with the variables and one without the variables, and then you look at the residual sum of squares, and basically when you get rid of variables, the residual sum of squares should go up. Now how much does it go up? This is the key. If it goes up a lot, then you will reject. If it goes up a little, you won't. So you look at the constrained residual sum of squares, which is high, subtract the unconstrained residual sum of squares, which is low, and then you divide this by the number of constraints, which would be here 4. And then in the denominator you have the unconstrained residual sum of squares divided by t minus k or something. Yeah, exactly. So, and then that would be a f statistic with m and t minus k degrees of freedom, and you would reject the null.
This analysis applicable for every country data, and he uses the European data?
This is only British data, UK. We had, and when I gave the course on econometrics to State Bank, we had them run the same exercise on all the countries, and you get different results in different countries. Each country has its own. You can also run this for Pakistan. Of course, you don't have quarterly data in most cases, so things are a little bit different. Okay, so he says that the most interesting result is that 24 cannot be rejected. If we test all the restrictions, so on statistical grounds, you see this is 24. So 24 is a very simple model, and In the unconstrained form, you would put C2 minus 4 on the other side. Yt would be replaced by Yt minus 4. And that is what was run actually, the unconstrained form. The big model, the encompassing model, has unconstrained, and then you test the constraints. So you test, is it true that the coefficient of Yt is negative and opposite of coefficient of Yt minus 4? And there are many other, the coefficient of Ct minus 4 should be close to 1, and so on. So there are many constraints, you put them all in and you test, are these constraints satisfied? You find that you cannot reject the null hypothesis of these constraints. So the data, whereas the other two models impose constraints which can be rejected. So as a result, we conclude that this is the best fitting model. Now then, the Henry paper goes on to analyze why we selected the model W, which is in fact the worst model from a economic point of view, economic theory point of view. Why? Well, if you look at 24, again it has the same problem that we were discussing with the wall model, that suppose that we are in long run equilibrium and income is stationary, then delta 4 of Yt will be 0 because income is not changing. Delta 1, delta 4 of Yt will also be 0, but delta 4 Ct will be 78, which means that consumption will keep on increasing by 78 units. So again, this model makes no economic sense. So वो तो फिर W model नहीं होगा ना. But if you were doing real econometrics, you would say this model with a constant makes no sense because it implies long-run behavior which is not compatible with stationarity. So we should run this model without the regression. Now then, what would happen is that since this constant is highly significant, 78.5 with 10.1, so that means that the model would be strongly misspecified, because basically you have a model in which the data is pointing to a line which has an intercept, and you are fitting a line through the origin. So that's a bad thing to do. So you should do something different, that will achieve your theoretical stationarity, but it will not fit the data. So these two things are simultaneously necessary, that you need to have a match to theory, but also you need to have a match to the data. So if this data constant was not significant, then we would be very happy to set it equal to 0 and say that this is the correct model. But if this model has a significant constant, then setting it equal to 0 is just a wrong strategy, but necessary from theoretical point of view. So now the Henry is now trying to find out why the worst model theoretically is the best model statistically. So now then he goes on and formulates the error correction model, which we may or may not study next time. I will think about what is the next important thing to do. But what Henry fails to understand about his own article, he says that if we use seasonally adjusted data and we do the same analysis, we come up with the opposite ranking. The Henry model comes out the best and B and W come out worst. So the lesson from this is that the statistical ranking of models does not matter very much. And in fact, this is the thing that I have also mentioned in my paper on methodological mistakes, which you should read at some point. Actually, there's a videotape lecture on that as well. Methodological mistakes and econometric consequences, in which I have shown that the methodology of econometrics is based on positivist ideas. It is nominalist, which means that it looks at names of things and doesn't look at the reality, and that's why it is seriously mistaken. You are looking for the best fitting model, but almost always the best fitting model will lead you to a fit which is produced by chance and not by reality. So what we are looking for is a good fit which is produced by a real factor instead of the best fit. Yes, that's the ideal, that's what Henry recommends, but it tends not to happen because econometricians are working too hard to find a good fit. And because they work too hard, they almost always end up finding the wrong fit. So you shouldn't work too hard in the sense that you take a model, you estimate it, and that's it. If you work too hard, like you see, you start with a linear model, it doesn't fit, so you add a quadratic triangle, that doesn't fit, so you add a cubic. Eventually you will create a good fit, but the fit will be meaningless because it will not be able to forecast. So what I was saying is that there are many places in which, if you look at the three models and you look at their forecast performance, then you find that the Henry model doesn't forecast well because it is not real. Basically, this is the main point of my methodological mistakes. This is one of the main points of this paper, that people have been running forecast tests. Okay, so given your model, here is a method of forecasting: exponential smoothing, linear regression, box-Cox, etc., etc., etc. So which model is best? Which forecasting technique is best? So they ran actually 3 major competitions where people all around the world were asked to send in their forecasting method, and then they would take 1000 time series and they would apply the forecasting method and they would see which works best. Now this is exactly what the nominalist way of thinking leads you to believe, but it will lead to nonsense results, because basically, according to the realist idea, the forecasting technique which will work best is the one which matches the real mechanism which is generating the data. So whether it's Box-Jenkins or whether it's time trend, you cannot compare these methods, because what you need to do is to compare the method with the real model, which is not there in the data, which is what is driving the data. And that comparison has not been made. So what will happen is the results will be random. And that is exactly what happened in the forecasting test, that sometimes something will be good, other time other thing will be good. On the first half of the data, one technique works best. The second half, the other techniques works best. In this series, this one works best. In that series. So no results. And ultimately, after 3 rounds of competition, they stopped doing it because they say, we learned nothing from it. And why don't we learn anything from it? Because they are looking in the wrong place. They are trying to find the technique which will forecast best. There is no such thing, because a technique will forecast good only if it matches the reality. The reality is not there in the data, so you cannot assess. So for each data set, you have to look, what is this data set? You can't look at the data set as just a list of numbers, because that doesn't explain you have to see what is the real process which generated this data set. So you see, there are 2 things. One is that you can take a model and destroy it statistically without knowing anything about reality. So this is what we are going to learn from the Henry paper: how to take a given model, how not to be deceived by econometricians. The next time the con man, the econometric hitman comes along, we'll be able to dodge the bullet. We'll say, here is your model, but this model is wrong. I can prove a model wrong without knowing reality. This is the important thing. I cannot, but to prove a model right, I have to know the reality. So proving a model wrong is not difficult. If I show that this is structurally unstable, then the model is wrong. I don't need to know that what is the real structure which generates the data.
How do we get the reality?
Oh, that's very difficult. That's a separate issue. But we will discuss that also. There are ways if you think about it. But with econometrics you can reject models without knowing reality, but you cannot accept models without knowing reality. So there are many illustrations of this principle, that the best fit model on seasonally adjusting is different from the unseasonally adjusted. When you forecast, the best fitting model produces the worst forecasts, and many other examples in this paper itself. So the conclusion is that the nominalist methodology is wrong, because you cannot rely on statistical fits to find the best model, but you can rely on statistical methods to reject the bad models. Okay, so that's all for today.